We'll discuss a non-Hohmann transfer, okay? So non-Hohmann transfer with common apps line, okay? So what you have is have this orbit. So what you're trying to do here is, this is orbit 1 and this is orbit 2, okay? And you're trying to get from orbit 1 to orbit 2. This is point A, and let's say this is point B. All right. Are you able to understand what we're trying to do here and why this is not a Hohmann transfer? These are still no, you can do a Hohmann transfer for non-circular orbits as well. See, our transfer is initiated at this point. It is not at periapsis or apoapsis. So how do you define a Hohmann transfer? A Hohmann transfer is the most efficient transfer between two coplanar orbits. This is still a coplanar orbit, but it may not be the most efficient. Okay, and we generally do the orbits for Hohmann transfer are concentric, right? They have the same center, which may not be the case for this one. Okay. But the apse line for this is the same. You remember what apse line is? So what is? No, that is not the apse line. Well, you can take that for now. Okay. All right. Let's do that. So you have the common apse line is, which means the periapsis and the apoapsis is in the same direction for both these orbits. Okay. Now, what do we need to know? Do you remember what is the goal in each of these? Whenever you're talking about orbital maneuvers, what are you interested in? And we discussed this. No? I want to again reiterate that whenever you're talking about orbital maneuvers, the one thing which is very important is your delta V. Okay? So at this point, you're going to fire your thrusters, right? You need to know what is the delta V required, the change in velocity, to go from this to this. So for you, how many impulses? This is again a impulse maneuver. How many impulses will you need? Your goal is to get from this orbit to this orbit. How many impulses would you need? You need 2 impulses. So what is going to happen is when you fire your thrusters from this, it's going to get out of this first orbit, right? But it's going to go into this transfer orbit. So if you let it be in this orbit, this is a common point, right? It's going to get there again. So it's not going to go into this orbit. You have to understand. It's going to come back to this point. So it will be somewhat like this. Okay. So you need one impulse here to get out of this orbit, and the other. Once you get here, you need another impulse to get into the second orbit. This is again a 2-impulse maneuver. Okay. And what you need to know is, you're always interested in this, because this delta V will tell you how much fuel you need for the spacecraft you're carrying. This delta V will essentially determine the design of the spacecraft actually. So how much load you can carry, What is the amount of fuel we should carry? Last class we looked at the change in mass, right? And we related that to the fuel. That is the amount of fuel you'll need to carry. Okay. So you have now RA is given by a squared over mu to 1 plus 1 over 1 plus E cosine theta A, and RB is given by, RB is given by a square over mu to 1 over cosine theta B. Okay, and theta A, theta B is nothing but the true anomaly at point A and B. And this is RA, this is RB. That's what you have. Now, E is equal to minus RA minus RB over RA cosine theta A. Okay. What is theta A and theta B for Hohmann transfer? What is theta A for Hohmann transfer? What is theta A for Hohmann transfer? You can look at it here and tell me. It is not a big deal. Where is the Hohmann transfer initiated? What? It's 0. It's not 1. It's initiated here, right? So theta, what is theta A? 0. It's initiated at the periapsis, right? So what is theta B for Hohmann transfer? 180, right? So if you just substitute that, you're going to get, for Hohmann transfer, I'll just mention it. E would be equal to minus RA RB over RA minus RB. Okay. Similarly, H is root of mu RA RB. So this is 2 over RA plus RB. delta V would be equal to delta V is equal to root of V2 minus V1 . Okay. It is to be V1 dot V1 plus V2 dot V2 minus 2 V1 dotted with V2. If V1 dotted with V2 gamma is the angle between V1 and V2, V1 dotted with V2 is equal to V1 V2 cosine of All right. So what do you understand what we did here? What I did here? See, when you're dealing with Hohmann transfer, the velocities are in the same direction, right? So your delta V, you don't really have to consider the vector aspect of it. The same, you can just, so when you're talking about Hohmann transfer, so this is your, let's say, V2, V1, right? So this would be delta V, right? So you can just pretty much ignore even if you just apply this, what is this angle between V1 and V2? It is 0, right? The angle between V1 and V2 is 0, correct? So if it is 0, this just becomes 1. So you're okay with just this being. If you just do this, you're going to end up with delta V. You don't need to take into consideration the angle. But when you're talking about a transfer like this, you have to talk about it in terms of vectors, okay? So let's say this is a local horizon, all right? Try to understand here, V1 would be something like this, okay? V1 corresponds to which orbit? V1 corresponds to the first orbit, okay? V2 would be something like this, right? And this would be your delta V. Got it? And this angle is delta gamma. Okay? So you have to understand that when you're doing this, you're just not changing the direction of V1, but you're increasing the magnitude as well here, right? If you just keep it, it'll do the same thing and get back to a similar orbit. Okay? If you want to get into a bigger orbit, then you'll have to change the magnitude and the direction. So if this is your local horizon, and let's say this is V1, so local horizon So this angle is gamma 1. This angle is gamma 2. Therefore, this angle is delta gamma. Here, just delta gamma is gamma 2 minus gamma 1. This you can see local. Okay. Do you remember what gamma is? What is gamma? Anyone? No? What is it called? Say, huh? You know what local horizon is? How do we define the local horizon? At any point, okay, if you join the center to that point, that is the local horizon. And the angle between the local horizon and the velocity vector is defined as gamma. You remember flight path angle? No? Flight path angle. Yeah. Anyways, so this is your delta gamma, okay? Change in that angle. Now if you, essentially what you're going to get here is delta V is equal to V1 square plus V2 square minus V1 V2 cosine of delta. Okay. And this is your formula for calculating delta V. All right. So let's quickly try to do a problem. This is impulse maneuver. Coplanar orbits. this coplanar orbits is actually very important. If we start discussing about out of plane or plane change maneuvers, things will get much more complicated. Okay. All right. So let's look at an example how to apply this. So you have a geocentric orbit. Right? This is your Earth. And what you're trying to do is you're trying to re-enter atmosphere. You understand what re-entering atmosphere is? Why do you re-enter atmosphere? Huh? Or you just want to burn up in the atmosphere. Right. So for example, this Russian space station was re-entered, right? It re-entered and it burned into, it fell into the ocean. Yeah. The Mir, it was called a Mir space station. All right. So this is a geocentric orbit, okay? All right. At this point, what you're going to do is you're going to initiate a orbit maneuver to re-enter. Okay. So let's say this is your local horizon. This is V1, this is V2, right? You have to go out and then come in. Okay. Right. This one? This is just Earth. So that is what it means. It is re-entering Earth. You see this path? It's actually re-entering Earth. So if you can think about so what is this? Atmosphere. Okay. So it's re-entering atmosphere. Yes. Yeah. It depends on, you can do it anyway. This is just one part. It depends on, for example, do you want it to enter this point where there is an ocean, or do you want to enter at this point where there is, let's say it's a populated city like New York, right? You want to determine that that point is very important, correct? So keep in mind, this is a geocentric orbit. It doesn't matter if you change the time, right? It's always going to be here relative to the Earth, because it's always there. It's a geocentric orbit. Okay. So what is given for this orbit? So R B 20,000 kilometers. So this is point C. Okay. And this is point B. C is kilometers, and RD is so orbit 1. This is a single impulse maneuver. Okay, I hope you realize that. Okay. E1 is equal to so let's identify the orbits. This is the first orbit, and of course this is the second orbit. H1 is 2 mu. RB, RC. Okay. And this is your point A. All right. Point A. RA is equal to due to square over. So we just use this formula. H square over mu into 1 over 1 plus e cosine theta a. Okay, this is theta a. I think we'll have to continue this in the next class. All right, let's pick it up in the next class. Okay. Next class is Monday. Any questions until now? It doesn't have to be just write it in between. It doesn't have to be, see, the thing with geocentric orbit is, it doesn't have to be a circular orbit, right? Why does it have to be circular orbit? As long as it gets here, it's going to stay there. If it's, the orbital period is